Excuse me. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you just bless our work today. Help us to just wrap up our thinking about Mission 2 and the material for Test 1, and just to make the most of this time, Lord. In your name I pray, Lord Jesus. Amen. So yeah, today I need to cover, the integral of a scalar function along a curve with respect to arc length. But we also have time for homework questions. You guys have any homework questions? Yes? How to start 30. So you just want to know how to start it, you don't want to know how to finish it?
I mean, I'd like to know that too.
Oh. Well, calculate the velocity, calculate the acceleration, right?
So you would take the derivative of that to get the velocity?
Mm-hmm.
That's what I did, but
Yeah, I mean, it's a position of particle at time t, so we differentiate to get the velocity. Then you differentiate again to get the acceleration. Now to find the tangential component, you need to calculate the unit tangent, right? So you take the velocity, you divide by the speed, right? And then you take the dot product of that with the acceleration. That gives you the tangential component. And then that actually then gives you enough information to find the normal component. So so logically you could kind of say that satisfies the problem. Of course, there's a more draconian reading of it which says, well, the word verify is there, so I must find n independent of this logic. And you can do that if you want, but that's a harder calculation, because then you actually have to find the n, which would be a pain here because of the nature of the speed. Yeah. But that might be a good exercise also to see that you could get through it, But if you don't have time, it's not the end of the world if you don't get the full verification in that problem, let's say.
you have office hours till 11:15.
I do, but, well, you can come to my office hours, see what happens. I'm not saying I won't help you. I'm just saying there are things happening at my office hours which might be in the way of you. So, anyway. But yes, everyone's welcome to come to office hours. Please do. I'm not joking. Go ahead. It's fine. I can. Well, anyway, other questions? Does that make sense? I mean, yeah. In other words, problem 30 is not that complicated. It's just kind of straightforward, just like, there's an example in the notes kind of like that, right? So, yeah. Other questions? Everybody else has finished mission 2 already? It's like, whatever. No? No, okay. Yeah. And tomorrow's math battle, right? Exciting, yes. So all that means is I'll divide you guys up into groups, and you'll have a group quiz to do in class. Yep. Yeah, sure, open notes. But there will be time pressure, so if you're just hunting through your notes for everything, it won't go well. But just as a matter of context, this math battle has been given as like a first test in a Calculus 3 course before. So it's essentially an in-class pre-test, group pre-test. I'll have a full solution to the math battle posted right after the math battle, because I've stolen these from someone else who's already typed solutions. Don't get used to that. There's not enough time in my life to type solutions, good grief. This is from someone else who lives a more simple existence where they have time to type up solutions, but anyway. But some of the problems on the math battle might look new. It'd be conceptually what we've already talked about, but you might not recognize some of the problem types, which I think is a very good thing, right? Because there's this kind of disgusting tendency in our modern education system that we ask you questions in the course evaluations. Was the test representative of the homework? This is a disgusting question for a university, because the test shouldn't be representative of your homework. The test should be, well, maybe representative is okay perhaps, but it shouldn't be your homework. Like, you should be tested on concepts, not the same problems that you already did. That's not really what's best. Now, I do test you on problems that you already did with numbers changed and stuff, but that's not really the higher goal of a university, which should be to educate people to think for themselves, not just regurgitate things you've already seen, right? You may not believe this, but that's actually what we should be doing. But there's more and more pressure not to do that with each passing year. So anyway, I digress. Yep.
I know in previous math battles, sometimes it's the time crunch, so you've added extra points, and they're going to be extra points.
Oh, I don't know about that, but you just do your best and see where it ends up. I don't remember if I put extra points in the math battles or not. There may or may not be. I don't remember. Let's see here. Other questions? Anybody dying to know the answers to the quiz questions yesterday? I can tell you the torsion on problem 2 was 0 because it's a circle in a plane. The curvature was 1/3 because it's a circle of radius 3. The arc length, the speed was the square root of 2 plus t squared, but you probably, if you didn't see that, you might not have seen that for problem 3. And then I got 15x minus y plus 6z equals to 72 for the equation of the plane, for what it's worth. But hey, I might have made a mistake doing that too, so don't read too much into it if you didn't get it. All right, but anyway. So, are we good? All right, let's get into the remaining. This is the last topic for, for test 1, right? So I think I'm going to start with a kind of weird point, which is, all right, so suppose we've got a path that goes from, let's say, gamma of A to gamma of B, all right? So I got a parametrization of some path, and so gamma is, it takes input a real time from A, or closed interval A to B, and it's given us some, well, it goes to this curve, which is a subset of R3, right? And this is an oriented curve, right? So let me just bring this to life with perhaps an example. So let's say gamma of t is, I don't know, t squared plus 1 cosine t e to the 3t. There. We haven't looked at that one yet. There's a curve. And what would you like the range of the, let's say for t what? Let's say 1 less than or equal to t less than or equal to, I don't know, 3. I regret my choices. I'm going to make this, instead of a 1, I'm going to make it a minus 1. All right? We all good? So I think we could all use a little bit more practice on this. Can you guys tell me what the parametrization is for the tangent line at time 0 to this curve? So what? What do we do? We calculate the derivative, right? The derivative at time t would give us what? We got ourselves a 2t minus sine t 3 e to the 3t, right? So that makes the derivative vector at time 0 equal to, in fact, 0, 0, 3, right? What's the parametrization for the tangent line? This should not be something that stops you. If I had given a 5-minute quiz on this, you should have been like, that was too much time, right? Because it's just, you take the position you want for the tangent vector, then time times the direction vector. Now, again, this would not be the colliding tangent line, right? This puts time 0. Oh, wait a minute. It happens to be the colliding tangent line. That's an accident. right? Because time 0 is the point of tangency, and it's also where the tangent line is at time 0, so they actually do collide there. And so here it is. The parameterization for the line would be, oh, what is gamma 0? Plug it in, right? 1, 1, 1, 1, 1, how boring. 1, 1, 1 plus t times 0, 0, 3. And there you have it. That is a parameterization for the tangent line at 0 to this curve. All right, so there's just a little review for you. All right? I would be shocked if I did not ask you on the test to find the parameterization of a tangent line to a space curve at some point, right? Like I would be surprised if that didn't come up on the test somewhere. All right, so so here's a question. So this is an oriented curve. All right, so this is describing C. What if you want to describe this curve going in the other direction? So instead, I want to go like this. All right, same. I mean, I'm just drawing it for the sake of perspective, as if it's a different curve. But I just want to go the same direction. So I want to do like the reversed curve. All right. And what if I want to make, just as a matter of, let me make sure I'm doing that right. I got to be careful about this because I sometimes, there's a couple different things you can do here. So this is just, so this is going to the same point set. All right, it's the same point set, but I would call the purple curve, this is a parameterization of minus c. So it's the curve in the opposite direction. It's a reversal. Well, there's a stupid, easy trick you can do, which is just, all you do is just take the original path that you had and feed it a plus b minus t. This will always work for a path which has its domain of the parameters as a to b. See how this works? Try it out. What happens when we plug in like gamma reversed of a? What happens? You get what? You get gamma of a plus b minus a, also known as b, right? And if we plug in b rather, into the reversed thing, we get gamma of, b's cancel, and we get a, right? So that's a good sign. The other thing that's interesting perhaps to look at is what happens if you compare the derivative at a point. Now there's where it gets a little bit tricky. See, because if this point right here is gamma of t, that makes it gamma reversed of what? How would I get that same point from the reversal? How would I? A plus b minus t. Exactly. Thank you. That's right. So if you wanted to compare the tangent vectors at that point, you should compare what? What's the derivative of gamma reversed with respect to t at a plus b minus t? It is, it's, goodness gracious, my bad. So it's d, it would be d gamma dt, right, at t. Oh, I'm sorry, guys. Let me stop writing this. My brain has broken. Just a second here. I don't think what I was writing was wrong. I should just project it. I have it written here nicely. So like here, so this, so just what you said, it would be d gamma dt is minus the d gamma reverse dt. Now, you can derive that from just differentiating the equation above. All right, by just differentiating the equation above and using the chain rule, right? Because if you think about, do you see that, guys? If we just differentiate this equation with respect to time, we get d gamma dt on this side. But on this side, we get the derivative of the function, right? But then we have to, by the chain rule, because the argument of the function is not t, we have to multiply by the derivative of the argument. What happens when you differentiate a plus b minus t? Well, you get minus 1, right? That's where that minus comes from. But you'd expected this already, right? Because you understand if the tangent vector to the curve looks like this, then surely the reversal's tangent vector looks the same but the opposite direction, right? That should be how it works. All right, so just to complete the thought here, what would be the reversal for my example 1? And I'm just going to write down the formula. So let's see here. A is equal to minus 1. B is equal to 3. So A plus B is 2. So I should basically, I'll do it schematically here, gamma of 2 minus t, right? And that means I have to substitute 2 minus t in the place of t everywhere, right? So that formula would be 2 minus t quantity squared plus 1, comma, cosine of 2 minus t, comma, e to the 3 parentheses 2 minus t. And there you go. That would be the reversal of that curve. Again, using the same parameter range. We good? I hope. All right, so there is another lengthy definition here. I'm trying to be disciplined to not write out on the board, as it would eat a chunk of class time and not be that interesting. But this is nevertheless an important concept which we should talk about together. So let's do that. You make no one's going to fall asleep, right? It's too early in the morning. So a reparametrization, what it is if you take a given path and you basically choose another parameterization. This is a reparametrization. We did this with arclength, but the concept is more general. A reparametrization is like a mapping from, let's say you're given a range of parameters that goes A1 to A1 to B1, and you have a function that goes from A1 to B1 to A2 to B2. For it to be a reparametrization, you want it to be such that it's increasing and it has a continuous inverse. And then the reparametrization of the curve is simply to replace t with u of t, right? So like we did this with u equal to arclength, for example. We did that. Now, if you do that, then you can relate the velocities of a curve and its reparametrization. And the relation of the velocities is pretty simple. It's the original velocity vector is just the new velocity vector times the rate of change of the reparametrization. So another way to look at this is a reparametrization, if you want to take a physical perspective, is parametrization is like a way to travel some path. You could think about it physically. It's a set of points, right? A reparametrization is going over the same set of points but with a different speed. Same set of points but different speed. So the velocity if you're going over the same set of points, but one speed versus another, you're going to have the same direction for your velocity vectors, but you're going to have different speed along the points. And that's what this equation says. Come on, right there. There are two kinds of reparametrizations. And I think I assumed this when I was just talking a minute ago, but you could either have du dt as positive, or you could have du dt as negative. If du dt is positive, you're still parameterizing c. C is an oriented curve, all right? But if your du dt, if your reparametrization map is negative, you would actually be reversing the parameterization with the reparametrization. That would be a parameterization of the reversal. For example, you could think of u equals to a plus b minus t in what we were just doing. Right? Think of that. U is equal to a plus b minus t in example 1. That's what just happened. Right? That's a reparametrization. The reversal is a reparametrization. So, there's that. So that brings us to the line integral of a scalar function, which I will make some pictures for because I don't have a picture in the notes, and you should see a picture. Oops. So let's get to that. Any questions before I erase all this? So I told college algebra yesterday, I said, don't make me laugh. What did they do? I forget what he said, but some guy in there said something hilarious. And then I laughed. And then you know what they did? They laughed at me for coughing. I said, you're horrible people. Horrible people. I was mostly joking. No, I was joking. I was joking. I've only really had the feeling that they were horrible people in college algebra once, and that was many years ago. I was really, really sick. I couldn't talk loud. And I told them at the start of class, please be quiet because I can't talk loud because I'm sick. And then they started talking, and then somebody in the middle of class is like, could you please be louder? I'm like, So then my wife had pity on me and went and bought me a mic. Then I used a mic, that's really disorienting as a teacher to use a mic and a microphone. Like you hear yourself speaking, it's bizarre. Okay, so line integral. Well, it's not a line integral. What's wrong with me? Integral with respect to arc length. All right. So we're given curve C, parametrized by, let's say, gamma, which is a mapping, let's say, from A comma B to C. All right. And I'll have to make the picture two-dimensional, all right, just for the sake of explaining what's going on. So here's a two-dimensional. I'll then hazard a three-dimensional picture, but let's suppose we're two-dimensional, and just to keep things relatively simple, I'm going to picture the curve as if it's in the xy plane, all right? Like that. Here's my curve. So here's maybe gamma of A. Over here is gamma of B. All right? And then we have in mind some kind of function. So we can visualize the function. And I'm just going to visualize the function. I'm going to assume the function's positive just for the sake of my picture not being like super complicated. So I'm going to draw the values of the function as if they're vertical. All right? So here's the function. It's big at the start. It's getting a little bit small. It's going down to 0 here for the convenience of my graph. And then I'm going to make it get bigger again because I can do that. And then here, and then here. And make it get smaller again because I can draw that. You're like, what if the function isn't good for drawing? I don't know. It's my example. Leave me alone. All right, so like here's the values of the function. Whee! Over the curve. All right. You got my meaning here? It's a sneaky snake, and that's a curtain that's above it, right? So then the question you might ask is, what's the area of that curtain? What's the area of this this blue vertical curved strip, yeah? And that's what the integral with respect to arc length calculates. Or another picture we could draw. You could have a curve like here, from gamma of A to gamma of B, right? And you could consider a continuous distribution of monkeys. I'm not sure I can draw monkeys. I should have chosen something I can draw. A continuous distribution of Pac-Man. So you got a big Pac-Man here, well, a medium-sized Pac-Man, right? And then you go a little bit further, and there's a bigger Pac-Man, all right? And then there's a wee tiny Pac-Man, and then a really, really small Pac-Man. All right, but then, the Pac-Man stays small, they're still small, and then it gets big again. And then it gets huge. And then small again, and then small. All right. So this is my best illustration of the idea of a density. So you could say that lambda is equal to d Pac-Man ds. It's the Pac-Man per unit arc length along the curve. All right. If you'd like me to make this less weird, think of these as like little bowling balls or beads or something. And we're talking about a wire of variable thickness. Then the question would be, what's the total mass of the wire? Yes, sir?
Is that the second one, is that on a plane, or is that still,
This is three-dimensional, and thank you. I'm missing a header. While we're at it, n-dimensional. You might wonder how I'm going to draw the picture. Here's how I draw that picture. x1, x2, xn. There you go. There's my n-dimensional picture. Now the thing is, we can give the same formula for arc length in all three of these. Integral with respect to arc length is integral over c of f ds. All right? And guess what that means? It's the integral from a to b of f of gamma vector of t times the magnitude of d gamma dt. This formula works in n dimensions, but don't worry, we're pretty much only going to do n equals 2 and n equals 3 in this course, right? But the fact of the matter is we have proved that arc length is a reasonable concept in n dimensions if you really look at our arguments. What did we prove, by the way? Does this all make sense? Notationally? It really does. What is this? That's the speed, right? It's the magnitude of the velocity. We differentiated the integral with respect to a varying bound, and we proved that that was ds dt. Right? We proved that that was ds dt. So what are we doing here? We're doing nothing more than taking the integral over ds and expressing it as an integral over dt. Because we know how to integrate the parameter, right? This is just an abstract concept. How do you actually calculate it? What's your program of calculating such a thing? Well, use the parametrization. We will use this idea again and again and again in this course. To calculate a geometric object, what we do is replace the object with its parametrization and calculate the integral of the object in view of the parametrization. Now this begs a question. How do I know that this integration doesn't depend on my choice of parametrization? I just got done telling you there's infinitely many choices of parametrization. What right do I have to say that that integral is not dependent on the parametrization, right? So there's a question you guys would never ask me, but it should be asked. It also should not be written on the board. I should use my projector because, you know, life is short. So here's the proof that if we used a different parametrization, it doesn't change the integral. And actually, we learned something else here beyond just that. You might worry that if we used a parameterization which reversed the direction of the curve, well, just think about this intuitively. If we reverse the direction of the curve for the parameterization, should that change that integral? If we change the parameterization of the integral, like the parameterization of c, should this change if I replaced, say, gamma with its reversal? If you think about it intuitively, it really shouldn't, right? Because we're just adding up areas. And if you add the areas from the start of the snake to the end of the snake, or if you add the areas from the end of the snake to the start of the snake, it should be the same area, right? If you've got a big curtain, you got one friend calculating its area from one end, you got another friend calculating the area starting at the other end, and they meet in the middle and then go to the other end, and then they get their walkie-talkies and compare. They shouldn't get different answers, right? Like, it shouldn't matter. I don't know why there's such a big curtain that they need walkie-talkies to measure the area, but anyway, just...
Is there signed
Is there signed area and signed volume? No. Well, yes. But let me say it this way. That is the fundamental difference between the double integral in here and the single integral. The single integral has a natural orientation. Like we learned in Calculus 1, integral from a to b is minus the integral from b to a. When we talk about double integrals, they're not oriented that way. Triple integrals also not oriented that way. However, surface integrals and line integrals are. But this is not one of. This is not an oriented integral, as I'm about to prove here. So, all right, if I can not cough. You know what? One more. Give me a second here. If you don't mind, I'm gonna. You know, cough drops are poorly labeled. Think about it. So, let's see here. So if we take this here, come on, man. All right, again, new laser. Oh, oops. Maybe that's the problem. Some idiot's been, oh, well, okay. It's discipline right there. Spare the rod, spoil the laser. So if we start with the integral done with respect to parameterization 1 and we reparameterize it, right? Look instead at the parameterization, like reparameterization, replacing t with u of t, right? So gamma 2 of u of t is the reparametrized curve. What happens? Well, I get this, right? Because remember that was the relation between the velocity. It's just the speed times the reparametrization. But then what? Well, then I can pull out this absolute value of du dt in that, right? And what are we looking at here? Think about it. Does this remind you of anything from Calculus 2, old end of Calculus 1? If we could cancel these dt's, right, what would we have? We'd have the integral over du, wouldn't we? But then we'd have to change the bounds. U substitution, right? This suggests a U substitution. And so, of course, then I need to break up into cases, because if du dt is positive, that means that u of a1 is a2 and u of b1 is b2. So when I do the U substitution, and by the way, the absolute value of a positive thing is the positive thing, right? So I just replace absolute value with du dt, and well, and then what? Notice that I have to, when I change from dt to du, I do what? I do the thing you guys forget to do. Well, not all of you. I should stop being so stereotypical. But stereotypes are useful, right? I've seen a lot. I mean, I've been teaching my children stereotypes this summer. Well, not really me. More Dude Perfect, but anyway. I'm a little bit concerned. My 6-year-old is like rage monstering a little bit too much sometimes. Like we just take a walk and he has to take a break every like quarter mile or so to like rage monster. It's kind of disturbing. But when a 6-year-old rage monsters, it's kind of hilarious. I don't know. At some point that's going to catch up with me. But anyway, so we're changing the bounds. We change the bounds, right? Lo and behold, that is exactly the scalar integral with respect to the second parameterization. So we change the parameterization, we still get the same integral. Yay. But what if it was orientation reversing? How does this calculation go? Well, if it was orientation reversing, then you get a minus from the absolute value, right? But the good news is if it's orientation reversing, it flips the bounds, because A1 goes to B2 and B1 goes to A2. So then I get a minus from this, but I also flip the bounds. To flip them back, I get back to there. So yay, the scalar integral with respect to arc length is orientation. It doesn't care about orientation. All right? Now, you might find this sentence to be a little bit suspicious. I say the scalar line integral of a function with no attachment to c is independent of the orientation of the curve. What do you think that might mean about this course? This is a very oddly specific sentence, isn't it? Maybe that means that later we'll be looking at a scalar integral where the thing we're integrating actually has an attachment to the curve. See, if the thing you're integrating actually is defined in terms of the curve, then this doesn't have to happen. But in as much as the scalar function is not curve dependent, this is a truism. A tautology, for you Math 200 students. Let's see here. Now, here's the formula. Here's the formula for the arc length in 3 dimensions. You take your function, you evaluate. Now here I should mention, this means, what I mean here is x, y, z in terms of t. All right, x, y, z in terms of t. And of course here I mean differentiate the formula for x, y, and z in terms of t. You square them, you take the square root, that's the speed. And you integrate that over time. That's the actual formula, right? So let me look at an example here, and then I'll put this projector away here. So here's one. One more thing. So if I had a helix, one of my favorite examples, right? R cosine t, R sine t is equal t. And I had that the mass per unit length was given by z. So like the mass density is dm dz. All right? So what would that look like? It would be something like that would look something like what? So it starts here, right? And then it's a helix, so it does one of these deals. My picture's never really quite accurate, but if it's, so like if the mass is dependent on, let's say the mass is dependent on the size of the wire, right? dm dz equals z. That means as z gets bigger, the mass per unit length gets bigger, right? So that might be something where it's starting out, well, pretty thin, but then as you go up, it's just getting, it's supposed to get bigger. My bad. Man! I should have stopped while I was ahead. Oh, see, now it's just not going to work. All right. I should have stopped down here. Here it looks okay. I think the thing is I'm having trouble making this. Oh, rats. I got sucked into the other one, didn't I? All right. Then it comes back around and it's bigger. It's supposed to get bigger. Oops. Wait a minute, what? All right, well. So that would be something like this. The mass per unit length is getting linearly bigger as you go up with z. All right? So the formula for something like that might be dm dz equals to z, all right? And then what would the mass of a helix like that be? And I cruelly put 0 to 4 pi, which if I was going to be true to my picture, 4 pi goes 2 times around, right? So if I was really going to be a stickler for being with my picture in my OCD, well, I'd need to write up here. So anyway, so here it is, z ds. Now, so here's a template for the formula, right? I integrate from 0 to 4 pi dt. Now what do I have to do? Z is equal to what for the helix? Z is equal to t. So I put t here. And this guy, the speed for the helix is constant. It works out to r squared plus 1. We've done that calculation before. And then this integral works out to this. So there's the mass of the helix, 8 pi squared, that. What's the arc length of the helix? Well, you know, to calculate arc length, you just do the scalar integral with respect to ds. So the other thing in all this calculation is it literally just drops back to the arc length calculation if you're just integrating f equal to 1. It just gives you arc length. And so that's why we get this, which works out to this. So if you have the arc length, right, the length of the curve, if you've got the total mass of the curve, what would it mean if you divided the total mass divided by the arc length? What would that be? Yeah, that would be the average mass per unit length. If you wanted to find that, you could do that. So more generally, if you want to calculate the average of a function along a curve, you can calculate the integral of that function along the curve with respect to arc length and divide by the length. That would be the average of the function. We defined average of a continuous function in Calculus 1 by like integral from a to b divided by b minus a. Remember that? It also would be like the average area under the graph y equals f of x from a to b, if you think back to that. This is a generalization of that idea, the average of a function along a curve in space. And so for the helix example, if I take the quotient of the total mass by the arc length, I get 2 pi. Wait a minute, I get what? 2 pi. Which I said is not hard. I said that's hardly surprising. I guess that makes sense. It starts out at 0, and then the mass per unit length gets all the way up to 4 pi at the end of it, right? So if you've got like a linearly increasing thing and it goes from 0 to 4 pi, making it be the average is not surprising. Now those of you who had physics, this might be more familiar to the idea I'm using, but yeah.
So is that function, like any green box, is that function at all?
This function?
Yeah.
That is a function of either xy or xyz, or, I mean, we could define this to be a function of like n variables. This would still make sense in n dimensions, but don't ask me to make the picture. Wait a minute, no, I had the picture. Oh, I erased it. Dang it. You know, that picture's not very, that's kind of a dishonest picture, is it? Well, I don't know. I mean, it's the best I can do. Now, I will eventually put away this projector, I promise. If you want to calculate like the geometric center of a curve, it's so-called centroid. Or if you wanted to, like, if you had a wire with variable, or if you just had a wire of constant density, right? If you have a wire of constant density and you want to balance it on one point, if that wire is rigid, if you wanted to balance on its center of mass, right? Then you could calculate the center of mass by doing these integrals. The centroid is the geometric center of a curve, which is also the center of mass if it has constant density. Now, if the mass density isn't constant, then the centroid and the center of mass can differ for a shape. But to do this, we have to integrate the density. So here, delta is dm ds in this definition. So that's the mass per unit arc length. So you integrate. So what this is really is the integral of x dm. This is really the integral of y dm. Notice that delta ds really is dm. That's the way to think about this. And like generically speaking, integral of x dm, integral of y dm, integral of z dm. This is x bar, this is y bar, this is z bar. For a Sorry guys, I don't know which button I'm pressing. So so here's just, what I'm putting in a box right here. This extends past this discussion. In physics in general, if you want to calculate the center of mass of an object, you need to integrate over the object the x function, the y function, the z function, weighted against the mass. So what kind of integral these are depends on what kind of object you're talking about. For a curve, it's an integral with respect to arc length, because that's how you integrate along a curve. But it could just as well be an integral over a two-dimensional. It could be an integral over a surface if you wanted to calculate the center of mass of a surface. But we don't know how to integrate over a surface yet, right? So we can't do that. If you want it to be the center of mass of a volume, then it should be an integral over a volume, right? But we don't know how to do that yet. My point is that this concept of center of mass, doing the calculating the so-called center of mass, this is a general thing from physics. Now in physics, one, you don't do integrals. Well, I do integrals. Some people don't do integrals. You can avoid integrals if you want to be lazy. But everyone covers this when it's a finite sum, right? I give you three masses at different points in space. I say find the center of mass of that 3 points. What do? You take the weighted average of them, right? What that amounts to is mass times position vector plus mass times position vector, and then you divide by the total mass. Well, that total mass becomes the integral over the density for us. And that sum of weighted position vectors becomes the integral, the x bar, y bar, z bar integral. But, oh, this isn't quite right. I should say that's my bad. You got to do 1 over the total mass. My bad. I'm sorry, guys. Total mass. All right, anyway, so just, sorry, I'll stop being a physics professor for a second here. I just wanted to tell you, there's a general story to tell here. Don't view these formulas in isolation. It's always the same thing. All right? There's just many different contexts. Any questions? No? So I wanted to actually calculate the center of mass for what is this here? Is it a helix again? Is this a helix? What do you guys think? X equals r cosine, y equals r sine, z equals h. What's that? Yeah, constant h means not a helix. 0 to pi means not a what? So we've got,
Half circle.
yeah, it's a half circle, right. So we've got the z equals h plane, and it's going where to where? It's going from what? Here to here. So the initial point was r, 0h, and then it goes to minus r, 0h, right? Over here at pi over 2, where are we?
0.
Yeah, 0, r, h, right? So if I draw the picture here, so I don't think you should be able to sketch carefully arbitrary paths in 3 dimensions, but this is the kind of path it would be good for you as a student if it was in your repertoire. If you were able to do this, this would be something that I would hope a Calc 3 student would be able to graph something like this leaving this course. Yeah, something like that. So of course, so this is the what? Z-axis. And what am I assuming? Did I not plug that in? Why are you doing this? Hello. Hello. Howdy. It's kind of persnickety. So I'm assuming h is positive in my picture, right? That wasn't given in the problem, I don't think. Where's the center of mass for this curve? Where's the centroid of the curve? I should say. Assuming it has, constant mass density, the centroid and the center of mass will be the same. Can you guys tell me?
Somewhere between the center and 0 or h.
Somewhere between the center, so like somewhere in this line, right? And it seems like probably, I would say closer to this side, if I had to guess. Now, in principle, if this was rigid and it was somehow like attached by invisible massless rods, that's the point where you could balance it, and it would just stay balanced, right? Or if you take such a thing and you throw it through space, it's going to rotate around its center of mass as it goes around. That's the physical significance of this thing. But so here's the calculation. Surprise, surprise, just like you told me, the x bar works out to 0 because when we integrate the, first of all, the arc length is easy here, right? It's a half circle, so it's pi r, that's the arc length, right? If it's a circle, you are allowed, in fact, I encourage you, unless the whole problem is show the arc length of this curve is 2 pi r. If that's the problem, and then you say, well, this is a circle, so its arc length is 2 pi r, then I will be annoyed. Because the point of that problem would have been for you to calculate the arc length of the circle. That's the whole problem, right? But ignoring that problem, in another problem, if you have a circle and you're trying to find its arc length, you are totally within bounds to write 2 pi times the angle subtended for that arc, right? Like you should know, 2 pi r, no, excuse me, wrong way. R times the angle subtended, right? S is equal to r theta, the change in theta. Like you can use that. You don't have to do that integral every time for that, we know arc length along a circle is my point. All right, so we know that a half circle has length pi r. Integral of x ds, well, okay, x is what? X is r cosine t, so I put that in there. And my ds, well, my ds is r dt here. So, because remember, x dot squared plus y dot squared plus z dot squared. Uh-oh. I was about to say uh-oh, but what's z dot? 0. Woohoo! All right, phew. So the x dot squared plus y dot squared is literally r squared sine squared, r squared cosine squared. You add them. The sine squared plus cosine squared is 1. The ds is literally r dt. All right? Now, so we end up integrating cosine from 0 to pi. But we know that integral is 0, right? How do I know that integral is 0? Did I do the fundamental theorem of calculus part 2? I don't think I did. I just looked at what cosine is. This is cosine. Cosine integrated from 0 to pi is 0 by symmetry. So now, of course, you could say, well, the integral of cosine is sine, and sine evaluates from 0 to pi to be 0 minus 0. Great. That's fine also. Anyway, that integral is 0. Now, the yds integral sine, that works out to 2. So we get 2r over pi. So let's see here, 2r. So basically, what's 2 over pi? It's about 2/3, right? So, ish, something like that. All right, you guys have any questions? No? All right. The arc length integral has properties that are pretty straightforward, like the integral of a sum is the sum of the integrals. You can pull a constant out. This is interesting. If you have the union of two curves, then the integral is the integral of the first curve plus the integral over the second curve. So like it's additive over unions of curves. That's kind of neat. But that's it for the notes, right? Now past this, if you look, I have a bunch of problems. You know, mathematicians are weird. They're really only happy if they have problems. You know? It's a funny thing. But in here, I would point out there's some good questions to think about, like, oh man, you know what I'm thinking of? Woo! Goodness, I should have told you to take your Dramamine. at the end of chapter 1, I actually have there's some nice problems. It would be healthy for you to just read through the problems at the end of chapter 1, because the solutions are posted on the website, right? So like there's some things in here that are common test questions that I sometimes ask. I'm trying to get to them. Like I'm talking specifically about like problems 17 through 20. Like these are really good problems to think about, because I've forgotten to teach this too much lately, but it's a kind of important idea. If you have a dot b equals to a dot c, does it follow b equals c? What if you have a dot b equals to a dot c for all vectors a? Does it follow for b equal to c? Do you understand the difference between these? It's a big difference between knowing that it's equals for one given a, right, versus knowing it is equal for all a. These are very different statements. One is true, one is false. And then similarly for the cross product, like what does cross product equality tell you? Is there like basically this series of 4 questions is asking you about, can you cancel? Is there like a cancellation kind of property for dot or cross products? And the answer is kind of no. Let me explain it to you like intuitively. Why is it that a dot b equals to a dot c for some vector a? Why does that not imply b equals c? Because having that a dot b equals, well, first of all, if a is 0, it tells you nothing. If a is non-zero, it only gives you information about the part of b and c which are in the direction of a. So it only implies that the component part of the vectors are equal in the a direction. Something similar happens with cross product, right? If 2 cross products are equal, what does it tell you? Well, it tells you something, right? It tells you more. It's a vector equation, right? It's not a scalar equation. There's more information there. But it doesn't give you any information about the directions perpendicular to A. Right? So it could be that B and C are equal in the directions perpendicular to A, but they're not equal in the directions parallel to A. If that was the case, this equation would still be true, and yet they would not be equal. That's what's at stake here. But anyway, you can look at those, and I have full solutions posted on the website. Ooh, problem 22 is actually kind of like, oh no, that's not the one. Problem 23 weirded me out when I first saw it. Use vectors to show that the diagonals of a parallelogram are orthogonal if and only if, this IFF is if and only if, the parallelogram is a rhombus. I gave this problem in the homework, like maybe the second year I taught Calc 3, and then I thought, no one's asked me about this problem, and like, they're gonna all be wrong. And then everybody had like the right answer, and it was the same right answer, and I was like, huh, this must be on the internet. Anyway, I was just pointing out the problems at the end of the chapter might be good for studying. What else is good for studying as I'm just kind of getting ahead of the game here a bit? Well, the math battle today is a self-contained, in-class pre-test you guys are going to work out, right? That's great. But I do, if you look at my course website here, see, now you know what that means. Isn't that great? But if you go down here eventually, I do have old tests, like, here's test 1 of whatever, 2014. So you can kind of get a sense of what a test looks like in here, its length, right? So this is probably somewhat representative. My quiz, I used to give just one quiz with each test. So the quiz was actually like the pre-test.